So I think that, electric aircraft, when they're on the market, like the S-30, they're going to win for the routes that they're capable of flying.
Right.
And then as the technology improves, eventually you'll get to the place where you can say, okay, like for these short flights, we can be all electric. We can remove the turbine system. We can, make the aircraft a little bit cheaper
Oh,
by doing
right.
that.
Yeah.
But you're also going to be pushing into those longer flights at the same time and saying, okay, like now we can do 300-mile flights with a hybrid aircraft. Now we can do 400-mile flights with a hybrid aircraft.
Right.
Um,
So let hybrids be the pioneer, and battery only can sort of come along behind it. Yeah.
That's how I see it. I think that, when the technology gets to that point, the short flights, electric only, that's going to be the way that we like really lower the cost of flying as much as we possibly can.
Yep.
And then, the hybrids, you will realize cost savings with the hybrid system as well, relative to like a fully conventional aircraft. And we'll just keep pushing that up to get the most range that we can.
Ben Stabler is the CTO at Heart Aerospace, a Los Angeles-based startup developing a hybrid battery electric regional aircraft. Prior to joining Heart, Ben was co-founder at Parallel Systems, a startup building battery electric rail vehicles for freight transportation, and spent 5 years at SpaceX, designing power systems for the Crew Dragon aircraft and leading the avionics software team. Ben is also the guest on today's episode of the Sky Zero podcast. Ben, yeah, thank you so much for joining us today. I really appreciate you coming on.
Yeah, thank you. Excited to be here.
Yeah, for sure. Me too. So I wanted to sort of start with like about you, and how you got into all of this. We heard a little bit about your bio just now, but tell us a little bit more about your background.
As you said earlier, I was at SpaceX for 5 years. I was working on the Dragon capsule, which is a manned space capsule. Got to work on Starship a little bit as well.
Cool.
So I was working on the actuators for the flaps for Starship, which allow it to sort of, act like a little bit of a lifting body as it comes through the atmosphere, and then sort of navigate to
Steer.
the landing.
Yeah.
Yeah. So that was really exciting. Working with pretty high power systems. So on Starship now, that's an electric system. So there's high voltage batteries, there's big electric motors, and that's really my background. Most of my roles have had something to do with motors or batteries or power systems. I've done that in automotive. I was at a couple startups that were doing battery electric road vehicles, motorbikes, fast cars, and then obviously worked on that at SpaceX on spaceships, which is kind of an odd one. And then after that, I founded Parallel with some other engineers from SpaceX, and we're working on rail vehicles. So in some ways, what I'm doing here at Heart is a continuation of a theme.
Yeah.
But
You're collecting
it's
them
also
all.
my
I
first.
guess it's boats next, right? I mean,
Yeah, boats next. But it's an exciting space to be in. It's moving super fast. Obviously, we're seeing success in electric vehicles on the road, huge advances in battery technology, improvements on the propulsion side as well,
Yeah.
electric motors.
Yep.
And so aviation is really the hardest of all of them
Yeah.
because you have really high power demands, and you also have really high energy demands, and you're incredibly mass constrained. So, what we're doing at Heart is, really the first baby step towards decarbonization in the aviation sector. And this is a huge, incredibly difficult problem. The technology doesn't exist today to build long-haul aircraft that are electric,
Right.
but it does exist to build, small regional aircraft that
Right.
are battery electric.
Right.
So that's really what we're trying to do.
Yep. Cool. So how did you find out about Heart? Like, how did you end up there? And and you may as well talk about your role too. Yeah.
Yeah. Well, so I'm the CTO at Heart. So Heart was started in California as part of Y Combinator in the Bay Area. And then the founder, Anders, moved the company to Sweden back in 2019. And the goal there was to, service a market that is, much more common in Northern Scandinavia than it is in the US.
Yep.
These sort of short regional
Small
flights, you
regionals.
see a lot more of those.
Mm-hmm.
And then also, leverage the aviation talent that exists in Sweden. So Sweden, a relatively small country, but
Saab.
has
Yep.
exactly, yeah, Saab and SKF and various other sort of like core industrial engineering companies, long lasting,
Yeah.
long lived.
Yep.
What is? um, so moved the company to Sweden and grew the company, and obviously Heart found market fit in a way that many of the other sort of regional electrified aviation startups struggled to. So really compelling product and story, but as the company grew and got deeper into the development of the product, realized just how challenging this engineering project is, right? It's not something where you can integrate batteries and electric motors that exist in the market today, because they just don't exist. All the technology has to be built from scratch.
Yep.
And really, when you're thinking about building the aircraft, integrating the aircraft, the battery weighs 30+% the mass of the dry aircraft. You have to really design that in from day one. So you have to design the aircraft from scratch. If you don't do that, you're never going to get the efficiencies that you want in the structural design of the aircraft, and get the performance that you want. So the focus of the company over time kind of shifted from what we originally saw ourselves as more of an integrator, and shifted towards a company that needed to be more vertically integrated. And so that's when Anders looked at where the company was, and where in the world you can find that sort of experience designing clean sheet vehicles, electric vehicles. And he really found himself pulled to LA, to the California ecosystem, particularly the LA ecosystem. And so I got involved with the company around that time, and now we've actually shifted all of our engineering operations and our headquarters here to LA.
Right, which was big news. And it's interesting, you talk about it. Oh, we started out as an integrator, and now we think ourselves as more vertically integrated. Like, I mean, to me, yeah, I totally get that. I mean, most of the aviation community today is built around, I make this and you make that, and somebody else integrates. There's airframers and propulsion companies, but yeah, I think I agree with your premise that that's not going to work, right? And so at some point, okay, interesting. And I can also see why California, you spelled it out, but that was my guess, right? You've got Tesla, you've got SpaceX. If there's two companies doing clean sheet, throwing everything away and starting from scratch, it's those, right?
Yeah.
So how might you absorb some of that talent? Okay.
And by the way, when you look at the industry, today there is a lot of disaggregation, right? The big players, outsource a lot of the design of, the avionics and propulsion and even structural manufacturing in some cases. That's not how they started out, and when the big names today were sort of developing their aircraft, the first time around, they were much more vertically integrated.
Right.
And so what we're doing is not really you sort of mentioned throwing it out and starting from scratch. It's not really the intent of what we're doing. It's we're kind of responding to this technology paradigm shift, and you have to have that level of design ownership, that level of vertical integration to really get the design right when you have this big sort of like foundational technology shift. And that's what we're doing.
Awesome. So I kind of want to talk about the ES30 powertrain next. And I think you guys stand out, right? Like if you think about the eVTOLs, it's all sort of battery electric, and which kind of in the vein of the ES19 in a way, right? The previous aircraft. And then you've got other players like your Volteros and not so much Viridian, but definitely Ampere, parallel hybrids. So I think, well, technically, Voltero often flies independent hybrids now, but they're talking about going towards a parallel hybrid for where they're going with the Casio. So a lot of folks are sort of moving in that direction. But you guys, I really like the movement between the ES19 and the ES30, but I have to imagine that there was conversations about that, right? Like, and how we got there and everything. So do you want to start by, like, I'm kind of hinting at all this stuff. Like, how would you tell the story of the ES30 powertrain and how you got to where you are?
Yeah. Well, we see the ES30 as an aircraft that can drop in, you know, pretty directly to existing airline operations for these, you know, shorter regional flights and be a workhorse of these kind of, you know, short regional routes. And so, you know, to achieve that, you need to have, you know, first of all, really good economics. So that's really our focus. Pretty much everything we do is focused on how do you get really good economics. And so, you know, passenger count is an important factor there. You know, even with the ES19, you know, our goal was to basically push the passenger count as high as we could, push the range as high as we could, within the Part 23 sort of limitations. And you know what we found as we did that is that, you know, we were left with an aircraft that was, you know, somewhat compromised. You know, really mass constrained with battery technology that exists today. If you try and stay within the Part 23 mass budget, and your economics, you know, in a you know 19-seater are also, you know, pretty challenged. And so that pushed us into Part 25. And so, you know, within the Part 25 framework, the ES30 really represents what we think is the largest aircraft that you can build with battery technology that exists today that makes sense. You know, your range for your electric vehicle is somewhat independent of the size of the aircraft. You know, if you have a 6-seater or a 19-seater or a 30-seater, your achievable range is about the same. It's, you know, it's sort of in the range of 125, 200 miles, which is where we're sitting right now.
Okay.
And that's because the mass of the battery is so dominant. You know, if you want to double the range, put twice as big a battery in, the entire aircraft needs to grow. You know, maybe not twice as much, but almost twice as much.
Right.
And then your passenger sort of payload mass fraction really shrinks down. So that's what's driving us. And if you build a bigger aircraft, if you try to build a 70-seater or a 100-seater that's battery electric that has a range of, you know, 120 to 200 miles, that doesn't make any sense, right? You know, aircraft that are 100 seats, they need to be going, you know, 400 miles, 500 miles, 600 miles to make sense to the airline.
Sort of economically, yeah.
Yeah. So that's where we sit. And obviously, as battery technology improves, you know, so that's the, you know, the sort of the basis for the ES30 sizing. The ES30 is a hybrid, and it's a hybrid so that you can meet the Part 25 and, you know, IFR requirements using you know, conventional fuel, which is obviously much more energy dense than the battery. If you try to meet those requirements with, you know, purely battery powered aircraft like the S19 was, you end up carrying a huge mass of battery that, you know, gets used maybe 1 in 100 flights. So it's really inefficient to do that. You're carrying that mass around for every single flight, and you're using it 1% of the time.
So what about,
so we carry that.
When you say IFR, I think we're getting into like, oh, how much reserve do I need? And when you say the different, like Part 23 and 25, like I think I vaguely know that Part 25 is like transport category, but can you break it down a little bit? Like, what is it about the jump to 25 or IFR that means you need a bigger battery? Is it just that reserve, or is it something else?
Yeah. So the part, the IFR reserves are 45 minutes of flight time plus the distance to your alternate airport.
Oh, okay.
So, you know, we typically use something like 100 miles as a sort of a nominal distance to your alternate airport. Obviously, it depends on the route that you're flying. So your energy reserves going to depend on a specific route. But even if you just look at the 45 minutes, that's similar to the average flight time for, you know, one of our flights, or even in some cases longer. So it's a huge amount of energy that you end up carrying if you try to carry that in the battery.
Yep.
And you're right. So Part 25 is a transport category airplane. So that's, you know, your 737s, your A320s of the world. Part 23 is normal category. So if you like a Cessna or you know, a small aircraft. So the 19-seater ES19 was designed to be like basically on the upper end of the
fits into
category.
fits into the bottom.
Yeah,
Okay, into the top of 23. So 25 would include like a Q400 or an ES19.
correct.
Sorry, you guys are the ES19. I guess I mean
Yeah.
E195 or something like that. Okay,
Yep,
got
exactly.
it.
Yeah.
They're all in there.
And the safety requirements for Part 25 aircraft are higher. It's a more challenging category to certify an aircraft in because obviously the expectation is that you're, typically carrying, paying members of the public, in regular scheduled airline operations.
Okay, so we've touched on a number of things. I think of you guys as an independent hybrid as opposed to, say, a parallel hybrid, right? Or a series hybrid, right? And if series is, there's a combustion engine somewhere, but all it's doing is charging a battery. That, in my mind, I think that's serial. Parallel is like, they're both spinning the shaft, the drive shaft at the same time, or the propeller in this case, whether it's the battery in the electric motor or the internal combustion engine, but they can both do it. But I think of you guys as another thing. You have both at the same time, which is cool, right? And like I said, I like it. Like I could immediately see it and like kind of understand it, which I liked. But what trade-offs does that bring? Like what don't we know about what an independent hybrid does to the decisions you're making as an engineering team?
Yeah, so there's a couple different things that we're looking for. So one of them is, how do we build a really reliable aircraft? So safety obviously is of extreme import. So the nice thing about having the independent hybrid is that you have a turbine, you have an electric motor, you can run either of those systems, you can run both of those systems, and they're largely, as the name says, independent. If you have a fault of some kind in your electric powertrain, obviously there's levels of redundancy there to sort of reduce the probability of that. But if you were to have a fault, your turbine, doesn't really need to know about that. It can sort of operate independently. So that's really exciting to us.
Should help with certification too, right? I mean, you just choose a certified powertrain, and hopefully that helps, I imagine.
Yeah, exactly. So that's the second part here. So the turbine, on the wing in our independent hybrid configuration is very similar to how the turbine is installed in other aircraft. So it's an existing turbine that we're using, and it's mounted, in a fairly conventional way. And so from the perspective of the turbine, there's really not that much new about our aircraft, compared to any other aircraft that you might be flying today.
Which makes regulators happy. Yep.
Yeah. So there's a lot of really good things about it. Now, obviously, the efficiency of the aircraft is also really important. We want to get the most range that we can out of the batteries. And whether we're running on battery or on fuel, we want to use the least amount of energy because that's obviously a driver for the cost of operating the aircraft. So with this configuration with the independent powertrains, there is a trade-off there, right? Because you've got additional drag from having additional nacelles and additional propellers on the aircraft. So we're really working pretty hard here on continuing to improve the propulsion configuration for the aircraft, and it's we're pretty early into this. There are no aircraft out there right now which are hybrid you can buy today.
Correct.
So we're like really on the cutting edge here, and continuing to explore, how do we continue to improve the efficiency, improve the reliability of this propulsion configuration, just build a better aircraft.
So right, I mean, so drag, obviously. I mean, that seems to me like it would be the obvious one. Maybe a weight penalty. You're carrying around some not dead mass, but I guess it depends on how often you see it operating in which use case. Like if it's going to be operating on battery, sort of 60% of the time, then that turbine is maybe dead weight. But is it the other way around though? Like if you're operating with the turbine most of the time, is the battery system dead weight? Or I don't know. How do you think about it in that way?
Yeah, well, we think that our customers will, typically be operating in the electric mode and try to operate in the electric mode because the economics are going to be best there. So that's what we think our customers will try to do. So you need to carry reserve energy for this IFR minimum, right? Yep. So the 45 minutes plus your distance to your alternate. So you can do that by carrying additional battery, or you can do it by carrying. In our case, we have the additional turbines and the fuel. And because the fuel is so much more energy dense than the battery, even with the weight of the turbines, we're still very much the advantage is very strong to carry the turbines and the fuel rather than the battery.
Got
So
it.
that's how we're making that trade off.
Yep. Got it. But you mentioned the drag first, so I imagine it's drag
Yeah.
over mass in terms of the hit that they're bringing to the performance penalty.
Yeah. So the drag is obviously significant. That's part of the equation. For sort of optimizing the aircraft configuration. And so there's you mentioned earlier there's a number of different ways that you can do a hybrid configuration. You can do a series hybrid, for example. Series hybrids, which we've had various configurations in the past, which have looked at the series hybrid, and in that case you have the turbine with a generator, and then that communicates electric power to the nacelles where you have thrust produced by another electric motor. So in that case, you only have 2 propellers rather than 4 propellers, right? So there's a drag advantage there, and obviously there's other trade-offs associated with that configuration. So yeah, so obviously the goal is to generate the best economics for the aircraft. We want to minimize the total operating cost, which is a function of drag, and it's a function of the size of the battery that you have and the mass of the aircraft. And so that's what we're focused on, is like, how do we achieve that?
Cool. So one of the questions I sometimes think to myself about is, and apologies if this is a rabbit hole, but how independent is independent? Like when some of the hybrid systems that we see, I think like Electra, definitely in that series configuration, ES2, ES9, very much the generator has to be running pretty well all of the time, but that's more of a function of battery size. I assume ES19 did not have to have a combustion engine to fly. And I assume that means you guys had already solved significant engineering challenges around pneumatics, hydraulic systems, de-icing, HVAC, like all of the things. But yeah, I guess answer my question instead of me daydreaming like I normally do. How independent is independent? Like,
You've hit on a really good point, which is that it's not as easy as just taking out the turbines and replacing them with electric motors. And this is true of anyone who's working on electric aircraft. There's so many systems in an aircraft today which are powered by the turbines, right? So the pressurization of the cabin is powered by most aircraft that bleed air from the turbine, and the flight controls in most aircraft is most turbine aircraft is hydraulic, and the hydraulics are pressurized by the turbine. And so if you remove the turbine, or in our case, you still have the turbine, but you're not using it all the time, you don't have those systems available. So you need to produce those things in some other way, right? So our flight controls are going to be electric. We're going to have a sort of distributed electric flight control system. Our cabin pressurization is going to be electric as well. We have a really big battery, which is helpful. And by the way, you're seeing this trend in conventional aircraft as well. So the 787, adopts several of these systems for sort of secondary flight controls and systems related to cabin environment control as well. And the reason that you switch from sort of your engine power supply to your electric power supply is a mass savings, right? If you don't have to run hydraulic lines through the aircraft, then that's a mass savings. It's also reliability savings.
Yep.
Obviously, there's been various incidents in the past where hydraulic lines have been ruptured, and if you rupture a hydraulic line, you can lose several systems at once. Electric systems are generally more robust to that. It can also be an efficiency improvement. So there is a general trend in the industry to try to get towards a more distributed. Exactly. Yeah.
Yeah. We had Ed Lovelace from Ampere on, and I asked him what's your favorite aircraft, and he said the 787 because he say it's like 1.4 megawatts and worth of electrified. I'm not sure if I've got the number right, but it's a lot and it's impressive. Yeah.
The scale of aircraft is always, you go from, our RES-30 is a relatively big plane when you stand next to it, but then you compare it to a 787 or an A350 or something like that, and it's tiny.
We'll get there.
But always incredible to like see the scale between small and big aircraft. So obviously the technology that we're looking at really forces us into some of those decisions. But we see it as a favorable decision overall. But it obviously it does just reflect, the challenge of going to a new power source, going to an electric aircraft. There's so many things that need to be rethought, re-optimized, because you're changing your propulsion system.
Yeah. I think of like the way you guys started with the, battery only ES19 sort of approach as kind of giving you a leg up in some of the ancillary systems, like I think everybody else kind of gets to kick that can down the road, which is a benefit to them, I guess. They don't have to deal with it, but you guys already have, or you're at least in progress on it already. So I don't know. I think it gives you kind of an interesting leg up. It's interesting. Yeah.
Yeah. We had to bite that bullet early. Obviously a lot of the eVTOL and advanced air mobility companies are tackling similar problems. Our aircraft is pressurized,
right.
Whereas some of those aircraft are not.
Right.
So there's different but similar challenges there.
One of them, which I love and won't name, but doesn't even have air conditioning. When you watch them on YouTube, the dude is wearing gloves when he's up there flying it, because like they don't even have HVAC yet, much less they have pressurized cabins. So and I don't know how de-icing is going to work, but to your point, carrier class, there's a lot more systems that you're going to have to think about, right? I don't. Mm-hmm. I should ask if you're doing, I forget, do you have landing gear? Well, I mean, obviously, but does it extend and retract?
Yep. So the prototype that we're flying next year, the X1, has fixed landing gear. So, when we release videos of that, you'll see the landing gear do not retract, but in the production aircraft, they will be retractable.
Yeah. Okay. Cool. So, right. So even more systems, right? And you guys will be forced to pioneer. On some level. Okay. Cool. All right. Okay. So this means you definitely also have to get good at charging, right? And a lot of the parallel folks and even some of the series folks aren't bothering. I'll ask them, do you intend to use CCS or GBT? And they're like, yeah, we're not doing it at all. Like you have to put gas in it in order to make it go. But you guys, if I remember right, and Hangar Day 2024 talked a fair amount about Charin, right? And the megawatt charging system. If I remember right, there was even like the triangular face of it, being plugged into an aircraft. So I mean, I don't know. Tell me about charging and how it's different on aviation to other things, and what's it like working with MCS so far?
Yeah. So we've done some demonstration projects. We've shown publicly some work on charging. So we're looking at MCS, megawatt charging standard. Our battery in the production aircraft is going to be, I'm not going to give the specific capacity, but it's going to be a little bit north of a megawatt hour.
Okay.
So a megawatt is, you have to charge faster than obviously than a electric car. Electric car charges are typically around the sort of 150 to 350 kilowatt range. We're going to want to charge, around a megawatt for our
so this is
mission.
3x the 333 or so, like roughly 3x automobile.
Yeah,
it's not 30 or 300x. It's 3x. Yeah.
Right. Exactly. Yeah, roughly 3x, and it's similar to the power level that you would charge a semi truck with, an electric semi truck on the road. And actually, our battery size is also very similar to a semi truck.
Yeah. Okay.
Which is quite interesting. So that will allow us to recharge after a typical mission. So we use, for a typical mission, we use something on the order of 125 miles, from, origin to destination. So sort of like ground distance. And then obviously the aircraft, it's climbing, it's consuming a lot of power, it's flying the cruise mission, then descending, and then there's some taxi time on either side. But our typical mission is 125 miles, and we'll be able to recharge after that mission in roughly 30 minutes.
Okay.
So that's obviously allows us to fit into conventional airport operations. A conventional turnaround is on the order of 30 to 45 minutes. So within that time period, you'll be able to recharge the battery, the energy that you've depleted over that flight, obviously standardizing on MCS gives us access to that ecosystem. There's a huge amount of work that's going into that for particularly trucks on the highway. So that technology, we can basically directly reuse that, and there's some tweaks for the aviation use case, but generally speaking, it's the same technology.
Yep. If I remember right, MCS is essentially CCS, but sort of scaled up. But so similar. Obviously the electrical specifications are much higher, but otherwise very similar to Char and CCS in the end. And so to your point, half an hour turnaround. So you're going to have to taxi, and well, obviously everybody has to taxi. So I guess just like with the gas engine aircraft, you're going to be pulling the fuel hose to it right away. Same thing with this. You're going to be getting the electrical, and we sort of saw that in action in the Hangar Day videos in 24. Okay, cool.
So we've tried to minimize the impact on airlines and airport operations. Obviously it's not exactly the same as a conventional fuel aircraft today. There is, you do need to get it hooked up relatively soon when you get to the gate if you want to have that full charge window. It's a hybrid aircraft, so there's also fuel ports. So depending on the mission that you're flying, if you're flying a hybrid mission where you're consuming both electricity and jet fuel, then you would need to fuel the aircraft as well. And then there's often aircraft, particularly at regional airports, are fueled by fuel trucks. Whereas the electric infrastructure, you can't put that on a truck because it needs to be plugged into the grid or a large battery.
Yep.
So that's going to be located probably close to the terminal so that you can plug it in when the aircraft arrives at the gate.
Right.
So there's a few differences here operationally, but really we're designing it to be as easy to integrate as we can for a typical airline.
Got it. I guess you could do a charging truck, but yeah,
you could.
It's a lot of batteries to throw at it.
More batteries.
Yeah. Batteries for your batteries at that point. Yep. Right. That makes sense the way you're thinking about it. So one question I've got, I don't know if you've taken a look at Joby's GEACS or GEACS system that they've been developing. Did you guys review other standards? I totally get it. I mean, to your point, Tesla Semi, MCS, I think Volvo, MCS, like so many of the trucking companies, I want to say Peterbilt, I'm not sure, I'm not super expert there. But from what I understand, a lot of the trucking industry has sort of said MCS all the way. So I can see the intelligence in like, this is a thing. It is obtainable. This is going to be commoditized. It's also going to be tested like crazy by others, right? Yay. But did you look at, did you think about any other standards or what was the selling factor? Was there a decision around that or was it a pretty quick call?
Yeah, so Joby is working on charging standards, and from what I understand, the emphasis there is on kind of the front end. So maybe on the back, the charging equipment is similar to what you would use in an MCS system, but on the front end they have redundancy so that you can charge multiple independent battery packs with less hardware on the vehicle, which is exciting, particularly if you have a smaller, lighter aircraft, and so the mass penalty of having the switch gear on the aircraft to sort of isolate the different packs is more expensive. And then the other thing that they have, which is really interesting, is the fluid port, so that you can use ground side cooling equipment to take heat out of the battery and the aircraft,
and take some mass out of your aircraft instead of having to have liquid cooling on board.
And then there's other I think Gamma did a white paper that you can read about where they sort of proposed a common charging standard, and I think Joby was not involved with that, but many of the other eVTOL companies were, and it was kind of similar to the Joby standard that you mentioned. And then I think that's turning into some kind of an industry standard or proposal right now. I think there's some drafts flying around in the industry on that. So it's quite an interesting challenge. I think many of the eVTOL companies have been doing a lot of work on that. For us, our optimization is a little bit different because obviously our peak power demand is lower than it would be for an eVTOL. We're a fixed wing aircraft, so our sort of peak power load is lower than if you need to sort of vertically take off. So that means that the batteries that we're looking at and the cooling system that we're looking at is a little bit different than a typical eVTOL. And the other thing is that our aircraft is just physically larger, so some of these systems that we're talking about, the penalty is lower to sort of include them in our aircraft.
Fair.
So we're exploring these options. I think that this technology is advancing quickly, and obviously airports are involved and thinking about how it affects their operations. So we're certainly paying attention to it and considering it in the trades that we're looking at.
Got it. Yep.
But yeah, right now we're looking at the MCS system.
Cool. There's a little bit of podcast time travel to do here because I'll be releasing the Joby episode soon, so you could not have watched it. But they're going to be talking about how they intend, to be. They really need to focus on, getting certified. Obviously, is my take from what I can tell. But I think they're interested in getting the standard out there more than they have in the past. Yeah. I think they've sort of always kind of wanted it with that one PDF that they put on X, and that's really it, and a single email address. I think they intend to do more. So watch this space, I guess. But of course you can't watch it yet because we're still putting the finishing touches on the editing. I'll just put that bird in your ear, and we can move on from it from there.
And I think it's really exciting how collaborative this industry is. Like the different players working on electrified aviation. There is a lot of cross-pollination. There is a lot of sort of collaboration on standards. I think Joby, some of the others, certainly thought leaders, and very proactive at getting these ideas out there and trying to work with others to advance the industry as a whole.
It's fun watching it for me right now, that's for sure. And I think part of what you're saying is part of why. Yep, no doubt. If you could get one free breakthrough, what challenge would you solve with it?
Well, I think you'll probably get the same answer from most people working on electric aviation. I mean, my thing would be, if we could get 600 to 1,000 watt hours per kilogram at the cell level or at the pack level, that would be amazing.
Yeah.
Would really enable a lot more in electrified aviation. I think most people would say that battery is the
no doubt
thing they would want to push forward.
There was a light on moment for me when I realized cars are sitting on the ground, Kyle. They don't have to use their energy storage to keep themselves in the air, right? And doing so via fixed wing, you get lift, which is nice, as opposed to having to do it all with a rotor. Great, but it still costs energy to keep it in the air. So every ounce counts, and it's just different. We had this tipping point moment, I think. With automotive, where it was, I was talking about this with Ed, BMW put out the i3, which was their series, hybrid automobile, right around the same time. Well, in order to solve a problem that was common of EVs back in that era, which is they've got 100 miles range, maybe. I've got an older Kia Soul EV at home, and it's got 111 miles range, and it's still going. We love it, but that's just not a lot. And BMW was like, we can solve this with a range extender, and they put a little, 3-cylinder engine in the trunk. And this is right around the time that the Model S comes out, and they're like, oh, you could have just put 1,000 laptop batteries in it instead, right? And so I think uninformed me just sort of assuming of course we're going to see the same thing in aviation, but
we will eventually.
Okay,
the batteries will get better, and then at some point you'll be able to build an ES30 equivalent that will be all electric, won't have the turbines on. And at the same time, we'll be sort of pushing up to the higher range, and the IFR reserves, being able to carry enough energy so that if you miss your approach and you need to fly to an alternate, and you're in inclement weather, and you don't have the ability to put the aircraft on the ground, this is a real challenge that automotive just doesn't have.
Right.
Like a typical driver might take their car down to 5%, 4%, 3% of the energy in the car, and that's totally fine. You can do that very safely.
That's right. Worst case, you pull over and you call an Uber, right? Yeah.
Exactly. Yeah. And you just can't do that with the aircraft. So you're always carrying this huge battery reserve or energy reserve in some form in order to protect against that fairly unusual case where you just can't land the aircraft because of weather, and you have to go fly to another destination. So that's a huge difference, and it's a real mass driver if you try to do that with just the battery.
Right.
So there's always going to be a category of air crash where the economics are really driven by that nominal flight, right? 99 out of 100 flights.
Right.
I'm flying within the capacity of the electric system, the battery. I can get the economics of the electric aircraft, and then 1 in 100 flights, or even more infrequently, I need to turn on that turbine, and so my economics are going to suffer on that 1% of my flights. But at least I don't have to carry that mass every single time. So that's why hybrid aviation, it's a more direct solution to the problem than it is
Yeah.
in automotive.
Yep.
My belief is that if it's possible to electrify the flight, so for example, these short distance 100-mile flights that we're looking at with the ES30, if it's possible to electrify it, that's going to be your cheapest overall system, right? Because relative to any other energy
Absolutely.
source, electricity
So much cheaper.
is it's going to be the cheapest. And then you have the batteries, you have the electric motors. The electric motors, relatively inexpensive as well, last for a long time.
Maintenance
Batteries
costs.
a little bit more expensive, a little bit more life limited, but overall you're still going to be in a better place than if you use another energy source, like whether it's conventional fuel or it's hydrogen or some other energy source where you have round trip inefficiencies that sort of drive the cost up. So I think that electric aircraft, when they're on the market, like the S30, they're going to win for the routes that they're capable of flying.
Right.
And then as the technology improves, eventually you'll get to the place where you can say, okay, like for these short flights we can be all electric. We can remove the turbine system. We can make the aircraft a little bit cheaper by doing that.
Yeah.
But you're also going to be pushing into those longer flights at the same time and saying, okay, like now we can do 300-mile flights with a hybrid aircraft. Now we can do 400-mile flights with a hybrid aircraft.
Right. So let hybrids be the pioneer, and battery only can sort of come along behind it. Yeah.
That's how I see it. I think that, when the technology gets to that point, the short flights, electric only, that's going to be the way that we like really lower the cost of flying as much as we possibly can.
Yep.
And then, the hybrids, you will realize cost savings with the hybrid system as well, relative to like a fully conventional aircraft. And we'll just keep pushing that up to get the most range that we can.
Cool. So 600 to 1,000. I mean, press release universe, Magnix, I guess, is talking about 400 watt hours per kilogram. I think CATL is talking about 500 watt hours per kilogram.
Yeah.
But that's press release land. I mean, no, but I don't know anyone who's actually getting to procure that anytime soon.
Yeah.
What are you seeing? I mean, what you're in there talking to manufacturers, talking to OEMs, like. Is there something on the horizon coming? Or sometimes I worry that as an industry, aviation's like demand won't be big enough to force the weight curve down as fast as the price curve has come down. Lithium batteries famously just get better and better every year on a price perspective, but the mass side is harder, right? So like, are we gonna? What are you seeing when you're talking to OEMs and providers there?
Well, automotive is driving both the cost and the mass of cells down. The energy density in cells is improving as a function of automotive demand. Cool. So that's really exciting. And I think that you're right. The reality is that the aviation demand for cells today is not large enough to really drive the innovation that we need. So that innovation is being driven by the automotive demand.
Yeah.
And that's really exciting because, as you say, that there are the press releases that we see. There are huge improvements happening all the time. And when we look at cells, there's like silicon-rich cells that are starting to hit the market now, that are going into some automotive applications. Price point's a little high, so they're available for aviation applications as well. There's some semi-solid state cells which are starting to get into pre-production. There's some solid state on the horizon, which is I don't know of anyone that's using solid state cells in aviation applications yet, but that's coming soon. Batteries, it typically takes quite a long time to go from your prototype to something that's manufacturable in volumes that
right
you can actually ship to customers
with good yields and everything else. Yep. We had a previous guest on that was talking about how the way he sees it, that energy battery density is sort of somewhat like a trade-off with safety, right? Like it kind of makes sense. I mean, just when you, on the face of it, the more energy in the battery, the more there might be a possibility of thermal runaway. But I don't know enough to be able to validate that. Like, what do you think?
It's a complicated topic. There's some chemistries that we're looking, the silicon-rich lithium-ion designs, some of those cells you're packing in more energy, but there is a safety compromise there. Like the not necessarily the energy emitted from the cell during a runaway event, but also the sort of like the rate, sort of the aggressiveness of the thermal event is higher. So for some technologies there's a trade-off. For some technologies, there's really promising results from some of the solid state concepts where you really don't see those highly aggressive thermal events. It's a really complex engineering challenge.
And you mentioned solid state too, right? Like solid state also has a function here. I take it those are safer. I guess there's less flammability because the electrolyte something. But this isn't my area. Yep.
Yeah, I mean, those cells are generally not in production. They're a little bit further out on the horizon, or the ones that are in production are not necessarily getting the cycle life or the discharge rates that are necessary. So there's, I would say that we're going to learn more about solid state cells over the next few years.
Yeah.
But there's a lot of different advances happening in different directions and different technologies, different areas, and so it's quite a rich landscape.
Do you see any other future possibilities for emissions reduction? I mean, we've talked a fair amount about 600 to 1,000 watt-hour kilogram batteries and how that's not immediate horizon, but we're seeing some improvements. To your point. I like how you talked about having hybrids sort of push the envelope and then battery electrics coming behind. Well, that's the way I phrase it anyway. But do you see other trends or other technologies that could be involved in reducing emissions in aviation?
These technologies that we're talking about really apply to the shorter distance flights. So regional and then short haul, at least for the next a few decades. That's the kind of area that we're playing in. For longer distance flights, there is some opportunity to employ hybrid systems to improve the efficiency of the engine, particularly around takeoff. And so there's some opportunity for hybrid to have an impact there. But as you get to longer and longer distance flights, the sort of marginal improvement that you get from the hybrid system becomes less, and you spend more of your time in cruise. From an emissions perspective, long haul is a real challenge. So there's various technologies in research and in various stages of development for that. There's obviously synthetic fuels, which if we can get to a good cost structure there, that could be really exciting. There's hydrogen, there's blended wing design. So Jet Zero, for example, is working on significant aerodynamic improvements to the aircraft to really reduce your emissions that way. So it's a really hard problem to solve, and I think there's a lot of interesting ideas and innovations going into it, but I think probably too early to tell what the outcome will be.
A couple of miracles needed for some of the SAF stuff, but maybe fewer. Hydrogen, it seems like a good number of miracles, but gosh, is it compelling given how much energy you can pack into a hydrogen atom. Cool.
Hydrogen is certainly interesting. There's definitely challenges there too, the volumetric density and also the handling of the fuel. It's an easier shift to add some electric charging stations at an airport than it is to support hydrogen plus conventional fuel.
Automotive has really struggled, right? Just keeping. I mean, I guess there's fewer airports than we would need gas stations. So fine, it's probably worth the research. But there's a couple of miracles in there for sure. What about lessons you've learned? Anything that you used to think was true, and throughout this journey or through your journey in your career, things that you used to think that were true, and now you don't see it that way anymore.
Well, I think that we talked about this a little bit earlier, but I think that vertical integration in the development process, and we're not talking about designing every single bolt, owning every single bolt that's on
Sure.
the aircraft. Like obviously there's a broad supply chain that we're leveraging, all levels of complexity.
Just the way you
From
said that, it makes me imagine that you have designed a bolt, though. at least one, maybe. But I follow your point, though. Yeah. Sorry. Keep going.
um, yeah, I personally have not designed a bolt. It's designed.
Yep. Got it.
But yeah, so what I really mean is owning the design, owning elements of the design that matter. And this is such a complicated aircraft. We're introducing new propulsion systems, the batteries, the electric motors. We're addressing the complexities that arise because of that. So we talked about the flight controls earlier and the environmental control system pressurization of the aircraft. There's structural challenges. How do you, where do you put the battery? How do you fit it in a way that's structurally efficient, that allows you to have the lightest, weighing an aircraft structure as well.
Mm-hmm.
So there's a huge number of nuances and complexities
Yeah.
in the development. And so like really having ownership as an organization of that full stack and being able to respond to discoveries as you prototype, as you fly aircraft, as you understand better the technology that you're building, and then be able to respond to that quickly, get back out on the test stand, within a week or within a few days,
Right.
with a new design and try something new.
Reducing your cycles there. Yeah. Being able to learn
Exactly.
faster. Yep.
Yeah. So, and I think that this is true about any radically new aircraft technology that you're introducing. And I think that, there's a strong and growing community of startups out there that are sort of tackling these challenges and building the skill set and building the organization to handle this. And I think that's really exciting for the industry as a whole. I think it's going to inject a lot of energy into the industry.
Cool. Awesome. What are you most proud of?
Well, I'm really excited about the X1, which is our prototype aircraft that's in Plattsburgh right now. I think the team has done really phenomenal work on that. When it flies, and we're hoping to fly in Q2 of next year, we're in integration and testing of the aircraft right now. When it flies, it will be the largest aircraft by mass, all electric aircraft.
Wow.
Ever flown.
Oh, wow.
So that's really exciting. It won't be the largest wingspan. I think Solar Impulse has us on that, but
Sure. Yeah.
but it is a big plane. So that's really exciting. So we're pushing hard to make that happen, and then obviously we're continuing to work on our future prototypes as well.
So you're testing X2 as battery only. I assumed it was going to be full independent hybrid, with the turboprops and everything.
X1 will be battery only.
Ah.
It's an all electric aircraft. Doesn't have the turbines. And then X2, which is our next prototype, will have the turbines as well and be fully hybrid.
Got it. Okay, that's cool. I live too close to Plattsburgh, New York, to not want to ask for. But I can only imagine that you would keep your first flights under wraps. So never mind. Yeah. I'll reach out for LinkedIn later or something.
You might see it, but you probably won't hear it.
Oh, that's a fair point. That's a really fair point. Okay, so we'll head into the lightning round now. So what is your favorite airplane?
Oh, well, there's a lot of airplanes I love. You probably get this answer a lot, but the SS-71 I think is fantastic airplane.
That's now the second time we've gotten that one. Yep.
I love that plane. I'm a big fan of Kelly Johnson. I've read most of the books about him. I'm a huge fan of his approach to, engineering in general. Just getting teams really close together.
Yeah.
Putting them right next to the wind tunnel. Just really trying to accelerate those feedback loops, and the results, obviously were incredible as well. He was building planes.
Yep.
There's one aircraft that he built in, I think under 100 days, from sort of kickoff of the project to first flight. Just
wow.
Incredible stories.
Oh my God.
And he did all of this obviously without, simulation tools that we have today.
Right. Computational fluid dynamics and none of that. Yeah.
Yeah.
Not even 3D design tools. Yeah.
Exactly. And the SR-71 obviously is an example of an aircraft that incredibly challenging if you were to approach that today.
Yeah.
There's few engineering teams in the world that I think could recreate his results on that.
Yep. Cool. What's your favorite airport?
My favorite airport, I have a private pilot, so not a serious pilot, but casual pilot. But I fly from LA into Catalina, and I think that's
very cool.
That's a pretty cool airport for people who aren't familiar. It's I think it's about 2,500 feet up in the air on a mesa. So when you fly into it, you're sort of flying over the cliffs of Catalina. And then they have a great little restaurant up at the top there, so you can sit there and eat a burger. And occasionally military planes will come and buzz it for fun. So
that's awesome. Out of Santa Monica or LAX, or there's lots of choices.
Santa Monica.
Yeah, cool. There is a Velis Electro that often shows up out of Santa Monica.
Yep, electric planes out there in the real world.
That was not yours. No. Okay, yeah, got it. Okay, cool. Yeah, so my next question, do you have any shout outs? Anything that's giving you joy right now that you want to talk about?
Anything that's giving me joy. I'm not sure. I didn't prepare for this one.
I imagine you're working a lot. So I don't know.
Yeah, I'm busy.
Yep.
Yeah, excited. We just moved into a new office here in Torrance in California, so I'm excited to be in the new space. A lot more room for hardware, so we're going to be building parts, building systems. So I guess that's what I'm excited about today.
Okay, that's cool. That's worth it.
Yeah.
And then, I guess just a final question. Where should we follow you? Should we check you out on LinkedIn or Twitter? Or where should we follow you?
Yeah, so we've got obviously our website, heartaerospace.com. We do post on LinkedIn. We have a YouTube channel, I believe. So we're trying to get some more material out there. We're going to have some videos of propulsion testing going up in the next few months.
Cool.
Obviously, we've got the flight of the X1 coming up. So, hoping to fly that in Q2 of next year. And then obviously we'll have some media around that. So, yeah, hoping to have a lot more to share in the next few months, and then obviously continuing to prototype and push forward.
Awesome. Ben, thank you so much for spending some time with us today. We really appreciate it. Great conversation.
Thank you. It's been a pleasure. Appreciate it.